Hi, and welcome to part 4 of our Flow360 training. Looking at our expanded visualization of the training structure, you can see we have now moved into the advanced topics session, and this session will provide an overview of solver settings and debugging divergence. For today's introduction training, we will start by discussing solver settings, including adaptive CFL, controlling convergence, and advanced simulations. Then we will discuss sources of divergence, how to visualize divergence location, different initialization strategies, and then conclude with suggested steps for debugging divergence. First, we will look at adaptive CFL and why it is important. Traditionally, with ramp CFL, you have to specify three things: the initial CFL value, the final CFL value, and the ramp over which that change happens. That requires experience and careful tuning. If the ramp is too aggressive, the simulation can diverge. We implemented adaptive CFL to remove most of this manual tuning and to avoid many time-stepping related divergence issues. Adaptive CFL is controlled primarily by the linear residual convergence, with extra logic to avoid diverged states. If the algorithm detects that the simulation is about to diverge at a particular pseudo-step, it goes back and reduces the CFL and tries again. This retry mechanism is what we call smart CFL cut, and it is part of the adaptive CFL algorithm by default. The main advantage of adaptive CFL is that you no longer need to control three ramp parameters. Instead, you provide a single input called the convergence limiting factor. This parameter controls how aggressive or conservative the CFL evolution will be. Conceptually, you can think of it like this. For a very conservative convergence limiting factor, the CFL increases slowly and the residuals drop more slowly. For a higher convergence limiting factor, the CFL grows faster, and the residuals tend to decrease more quickly, but the settings are less conservative. And you must pay closer attention to robustness and accuracy, especially for complex cases near separation. By default, the convergence limiting factor is set to a conservative value. This was chosen so that a wide variety of cases converge without requiring the user to tune settings. With the addition of the smart CFL cut logic, the default is likely more conservative than necessary for many production cases. In practice, for typical steady simulations, you can often increase this value moderately to speed up convergence, as long as you monitor residuals and solution behavior. One important detail is how residuals are interpreted. In Flow360, the linear residual is scaled by the nonlinear residual. That is why the linear residual often appears between 0 and 1. As long as the linear residual remains below 1, the simulation is still converging. If the linear residual rises above 1, it indicates a potential divergence trend. In that situation, adaptive CFL will respond by cutting the CFL to try to bring the residuals back down. Overall, adaptive CFL does not necessarily guarantee a faster convergence than a perfectly tuned ramp CFL, but it gives a more robust solution process with far less manual tuning and fewer opportunities for user error. Now let's move on to convergence speed more broadly. In any CFD solver, there is always a classic trade-off between robustness, speed, and accuracy, where you can pick two and it will have some impact on the third. In Flow360, this is somewhat similar. The primary driver for convergence speed is the adaptive CFL setting via the convergence limiting factor. Higher values can improve convergence speed but may reduce robustness or affect accuracy if pushed too far on complex flows. For steady simulations, the default absolute tolerances for residuals are typically sufficient. For example, the Navier-Stokes default is set at 1 times 10 to the minus 10 power, and turbulence residuals at 1 times 10 to the minus 8 power. These defaults generally do not need to be changed. For unsteady simulations, the recommendation is slightly different. Within each physical time step, it is usually sufficient to achieve around 2 orders of magnitude drop in the pseudo-step residuals. For example, if you are running a rotating propeller case with resolved blades, look for at least a 2 order of magnitude decrease in residuals within each time step. This is a reasonable starting point, and you can refine it based on how sensitive your forces and moments are. Here are some general recommendations for pseudo-step counts. For simple configurations such as an isolated aircraft on a coarse mesh, around 2,000 pseudo-steps is often sufficient. For unsteady cases of similar complexity, around 10 to 15 pseudo-steps per physical time step is a reasonable starting point. For moderate configurations with more complex flow features and medium meshes, you may need higher pseudo-step counts for both steady and unsteady runs. Around 3 to 5,000 for steady and 20 pseudo-steps per physical step for unsteady. For highly complex cases with large meshes, you can expect to need more pseudo-steps and more conservative CFL settings. Around 8 to 12,000 for steady and 30 to 35 pseudo-steps per physical step for unsteady. If you are running low Mach number cases, you can enable the low Mach preconditioner. For Mach numbers well below 1, the low Mach preconditioner can significantly reduce the number of pseudo-steps required. When you enable it, it is recommended to increase the number of linear iterations from the default of 30 to a slightly higher value, such as 50. This often improves the rate of convergence without a large cost penalty. Here is an example of the low Mach preconditioner working. The graph on the right shows how this improves convergence. Also, for improving the convergence of the turbulence solver, the equation evaluation frequency of the turbulence solver can be changed from 4 to 1. Next, we will look at some additional solver controls that affect robustness and accuracy. If you run transonic or high-speed cases and see convergence difficulties, it can help to turn on limiters. Enabling pressure, density, and velocity limiters in the Navier-Stokes equations can stabilize strong gradients, especially near shocks or high Mach regions such as propeller tips at high RPM. Another key control is the reducing numerical dissipation. The default kappa muscle value is more upwind and therefore more dissipative and robust. Changing kappa muscle to negative 0.33 moves the scheme toward a more central, less dissipative formulation, which improves accuracy but reduces numerical damping. For low Mach, high lift, or wake-sensitive cases, it is often beneficial to use a lower dissipation value to better resolve turbulent structures. For DDES cases, like rotor and blade resolve simulations, it is recommended to use low dissipation factor values for improved accuracy. Using a numerical dissipation value of 0.2 instead of the default of 1 with DDES activates the low dissipation scheme, which often gives more realistic wake structures and more accurate loads than a highly dissipative scheme. Here's an example of the same case with and without low dissipation. On the left, you can see there is no low dissipation, and the turbulent structures are somewhat under-resolved. On the right, with low dissipation turned on, the turbulent structures are much more resolved. Now we will discuss how to debug divergence in Flow360. When a case diverges, Flow360 marks it in the run status with an orange dot indicating that the simulation diverged. There are several common causes of a diverged simulation, including mesh issues, incompatible boundary conditions, overly aggressive time stepping, or initial conditions that are too far from the physically correct state. We will discuss more details for each of these causes. Some typical mesh issues that can cause divergence include very sharp pinch points in the geometry where surfaces come extremely close, producing poorly shaped cells, large area or aspect ratio jumps between neighboring cells, especially near leading edges, as indicated in the mesh here. Another reason could be under-resolved regions where strong source terms are applied, such as BET regions for rotor loads. If the mesh is too coarse, it may place source terms in only a few cells, causing very large gradients that the solver struggles to handle. Flow360 has a few methods for diagnosing divergence. In the Analysis tab, you can go to Convergence and turn on the min-max plot. This plot shows the minimum density, minimum pressure, maximum velocity, and similar quantities as a function of pseudo-step. If, for example, you see the maximum velocity suddenly jump to a very high value, this indicates that the local Mach number somewhere in the domain has become unphysically large, which is a strong sign of divergence. Flow360 also records the locations where these extreme values occur. The solver automatically saves points corresponding to the locations of minimum density, minimum pressure, and maximum velocity. It also exports slices around these locations. You can turn on these points and slices in the visualization interface to quickly identify where in the domain the problem is occurring. For example, if a slice at the divergence location reveals cells with extremely high aspect ratio or large area ratio near a leading edge, that is a mesh quality problem. In such a case, you should fix the mesh near that region before rerunning the simulation. In most of the cases, this automatic slice export is sufficient. In very rare edge cases where the slices are not informative enough, you can download the full volume solution, or the mesh, and inspect it manually in an external tool such as ParaView or TechPlot. Boundary conditions are another frequent cause of divergence. The two main examples of incompatible boundary conditions are either user error or the boundary conditions do not match the physics. For user error, it's difficult for us to differentiate between engineering intent and user error. This could include misnamed face grouping or mesh. Where boundary conditions do not match the physics, some examples include mistakenly setting a symmetry plane as a no-slip wall, assigning an outlet boundary as an inlet, or using non-physical values for pressure or mass flow rate. Mismatched units can also cause issues. If the mesh and boundary conditions look correct, initial conditions may be the issue. Flow360 provides several techniques for a more controlled initialization. You can use user-defined expressions for initial conditions on selected regions. For example, you can prescribe density, 3 velocity components, and pressure in a cylindrical region, representing the rotor wake in hover condition, based on a simple blade element estimate of induced velocity. This gives the solver a much better starting point than a uniform zero-velocity field. For internal flow simulations using mass inflow and outflow, it is often better to ramp the mass flow rather than imposing the final value immediately. You can specify a ramp over several pseudo-steps or iterations so that the solver gradually adjusts to the target flow rate. Another method is to fork from simpler, already converged cases. For example, if you have a complicated configuration near stall, you can first run a simpler case at a lower angle of attack to convergence, and then use that solution as the initial condition for the more challenging case. Similarly, for very complicated flow simulations, you may choose to run an initial first-order or more dissipative simulation to obtain a robust baseline, then fork to a higher order or lower dissipation setup once the flow is reasonably established. If a case diverges repeatedly and you cannot resolve it by adjusting mesh, boundary conditions, or initial conditions, you can also rerun the case and stop a few iterations before the divergence point. Export the solution fields at that stage and inspect flow variables and mesh quality around the problematic region. This often reveals the underlying issue. To summarize the debugging process, double-check boundary conditions and inputs for user errors, non-physical values, or incorrect units. Inspect the min-max plots to see whether divergence is caused by gradual growth or sudden spikes in key quantities, such as velocity or density. Check wall spacing, aspect ratios, and first layer thickness around suspected regions. If the physics is inherently challenging, consider more conservative adaptive CFL settings, enabling limiters for transonic regimes or revising initial conditions. For very complex cases, consider using a simpler precursor simulation and then forking, or starting with first order and then switching to a higher order or lower dissipation scheme. Before we wrap up, I will leave you with a few recommendations. For large arrow databases, a practical approach is to first run a subset of representative cases to determine good solver settings. For these test cases, you can experiment with more aggressive convergence limiting factors and pseudo-step counts, monitor residuals and forces, and then apply the tuned settings across the broader database. This helps you achieve reliable convergence while controlling computational cost and flex credit usage. If you encounter persistent divergence in specific cases after applying these guidelines, you can share the case ID with the support or application team so they can investigate further. With that, we have now concluded the fourth training session on the overview of solver settings, adaptive CFL, and divergence debugging. As you continue your onboarding, we recommend that you continue to use and reference our online documentation. We would also appreciate to hear your thoughts and feedback, so we can continue to make improvements and shape the development of Flow360.